In this video, we're going to talk about permutations. So we've talked about counting. We introduced the fundamental counting principle. Now we're going to talk about some special situations within the idea of counting possibilities. So in some situations when we're choosing options, trying to accomplish some type of task, we may have certain restrictions on how we can choose, the number of ways we can choose, and the way in which we choose. So a permutation is a way of choosing where we have an option to choose from. We have a certain number of items to choose from. No item is used more than once, and the goal is to put the items we've chosen in a specific order. So there's an arrangement to them, and the order matters. So for instance, say we're choosing two items. Item 1, item 2 is one ordering. Item 2, item 1 is another ordering. So if we change the ordering of the items we've chosen, then we have a different possible combination. So a permutation is an arrangement of items. We can't use anything more than once, and rearranging makes a difference. So each arrangement is considered separate and unique from each other arrangement. So an example of a permutation where we can use what we know about the fundamental counting principle. So suppose you need to arrange 5 textbooks along a small shelf. How many different ways can you arrange the books, assuming that the order makes a difference to you? So for instance, one ordering would be A to Z based on author, one would be Z to A based on author. Maybe you do A to Z based on the title, or Z to A based on the title. If we're talking about a permutation, each of those orderings is different. When we rearrange them, we have a different permutation. We have a different ordering of those particular items. Now, how could we apply the fundamental counting principle here? We'd have to think about this as a step-by-step process. So how many steps are in this process? There's 5 steps in this process. We're arranging 5 textbooks. So each of the steps is choosing which textbook goes in which place. So step 1 is choosing the first textbook. Step 2 is choosing the second textbook, all the way down to the 5th textbook, the one we place at the end of the shelf. Well, how many ways can we do each step? Well, because we're not reusing things, because we're arranging 5 books, there's not the same number of ways to choose each individual textbook. So we're going to have to go step by step in order. So think about the first book. So right now the shelf is empty. You're choosing the first book to put on the shelf. Well, you have 5 textbooks, right? So for the first spot on the shelf, when the shelf is empty, you have 5 possible books to choose from to put as your first book on the shelf. Okay, so 5 choices. So you pick a book, you put it on the shelf. Now you want to choose your second book. Well, you have to take into account that you now don't have the whole collection to choose from. You've already put one book at the very beginning. You had 5 choices to do that. For the second book, now you only have 4 more to choose from. And then the same thing for the third. Once you place that second book, now you've already placed 2 of them. So for the third book, you only have 3 choices to choose from. For the fourth book, you've already placed 3 of them. So you only have 2 choices to choose from. And then notice for the very last book, you're only going to have 1 left. So once you've already put 4 on the shelf, you're already locked in as to what has to be the last book. So 5 times 4 times 3 times 2 times 1. That's the number of ways we could perform each step in a process like this. This is a permutation. So we're arranging a sequence of items. We can't use an item more than once. In other words, once we make a book the first book, we can't use it as the second or the third book. Once it's in the list, once it's in the arrangement, we can't reuse it. And also we've determined that the order makes a difference. So if we rearrange the books, we have a different ordering. As long as those 2 criteria are satisfied, then this represents a permutation type problem. A permutation is a specific arrangement. So each of those arrangements is considered a permutation of those textbooks. So if we multiply the number of ways together that we can accomplish each step, that'll tell us how many arrangements there are. So 5 times 4 times 3 times 2 times 1. And that's going to give us 120 ways to arrange these textbooks. So even with just 5 textbooks, 120 different arrangements. Now suppose the order didn't matter to you. That's a different situation. We'll talk about that a little bit later. not in this section, in a different section. But we're specifically talking about situations here where the order matters. Rearrangement matters, rearrangement changes things. So this particular product, notice there's a very specific form to what's going on. 5 times 4 times 3 times 2 times 1. So we're multiplying whole numbers together, and each time we're decreasing the number we multiply by. So we start at 5, subtract 1, subtract 1, subtract 1, all the way down to where we get 1. So we're multiplying a sequence of integers together. This particular multiplication is called a factorial, and the notation is as follows. So we're going to look at the highest number. We're taking 5, and we're multiplying by all the integers less than 5 all the way down to 1. So the notation for that is actually the exclamation point symbol. So mathematically this has a meaning. So the way we read this is 5 factorial. And what this means is take 5 and then multiply all the integers, all the whole numbers less than 5, all the way down to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1. 6 factorial, for instance, 6 times 5 times 4 times 3 times 2 times 1. The reason we develop a notation for something like this is in order to deal with situations like this. This is a pretty common situation, determining how many ways we can arrange certain things. We do these kind of problems fairly often in real life. Having a notation like this is going to keep us from having to simplify things like that. So in general, in terms of defining in general what factorial means, so say n is a positive integer, so it's an integer, in other words, counting numbers, and it's a positive number. N factorial, for whatever that n is going to be n, so start with that number itself, subtract 1, multiply that, subtract 2 from it, in other words, we're stepping down by 1 each time, and we take the product of all those numbers all the way down till we're multiplying 2 and then multiplying 1. So regardless of how big n is, that sequence is going to look the same. We're going to start at n, multiply the next lowest integer, then the next lowest integer, all the way down until we multiply by 1. Now, by definition, 0 factorial is going to be 1. We don't really have a way of describing that other than just saying that's a definition, and it's going to allow us to deal with some special cases that we may run into. Now, most scientific and graphing calculators actually have a key or some type of operation built in for factorial. So rather than having to do 5 times 4 times 3 times 2 times 1, there's usually a way you can do that immediately on your calculator just using this notation. And we'll talk about where that is on your calculator in just a minute. But in a lot of cases, if we have something involving a factorial, we can simplify it without using a calculator. So I want to show you what that looks like. Now, before we do that, let me show you where you can find this button on your calculator. So I'll show you on the scientific one we use, and then I'll show you on the graphing calculator. So if you're using this particular calculator, okay, factorial is not immediately available right there on your buttons. There's nothing labeled with factorial, but it is there. I promise it's there. You're going to start with the number itself. So say we're doing the problem with the textbooks again. So it was 5 factorial. You're going to do the 5 first, and then the factorial is going to be under PRB. PRB stands for probability. So as I mentioned last section, the goal is to develop all of this in order to be able to do probability problems. So we're going to go under PRB. Okay? Look at option 3 right there. There's that exclamation point. So I'm going to scroll down to option 3. And then hit enter, and it's going to put it on the home row for me. So this says take 5 factorial. In other words, 5 times 4 times 3 times 2 times 1. If you hit enter, notice you get 120. Well, that was what we determined we were going to get if you multiplied that sequence of integers together. And then this confirms that that notation is going to give you the same thing. Now, what if you wanted to do 8 factorial divided by 5 factorial? Let's do this in the calculator first. So you can either do each of the numbers individually, or you can do it as one unit, which I would recommend doing that. In other words, type h factorial, and then instead of hitting enter, just hit the divide key and then type in 5 factorial. Your calculator is pretty smart, it can handle that. So 8, and then remember, go to PRB for probability, 8 factorial divided by 5 factorial. And there we go. That's going to simplify it down for us. Come on, there we go, 336. Now, how could we do this in another way? There's another way to do this. We want to think about what factorial actually represents. So remember, it represents a sequence of multiplying integers together, starting with the largest and then multiplying all the integers down to 1. Each factorial, each smaller factorial, is contained within a larger factorial. What do I mean by that? Well, for instance, we have 8 factorial divided by 5 factorial. I want you to think about what each of these represents. 8 factorial represents 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now 5 factorial represents 5 times 4 times 3 times 2 times 1. Think about what's in common. They have a 5 in common, they have a 4 in common, the 3, the 2, and then also the 1. Well, we have a name for that sequence of things they have in common. The name for that sequence of things they have in common is 5 factorial. So 8 factorial, which is definitely larger than 5 factorial, actually has 5 factorial as part of it. There's a way to demonstrate it. What I've done right here is I've pulled off individual factors, individual numbers being multiplied. So I've broken down 8 factorial just a little bit in order to get to a point where I can see what matches. In other words, take some of the individual things we're multiplying and just pull off the individual factors. So if we're taking 8 factorial, well, that's an 8 times a 7 times a 6 times 5 times 4 times 3 times 2 times 1. Remember, we have another name for that. We call that 5 factorial. So I can pull off these individual factors and then just leave the rest in this condensed form that we're writing as 5 factorial. Well, as long as all these numbers are being multiplied together, then I can reduce anything that matches in the numerator and in the denominator. That 5 factorial is what matches. So that can actually be canceled. We can reduce that because those divide out and give us a 1. Well, what are we left with then? We're left with 8 times 7 times 6. Well, according to the calculator, 8 factorial divided by 5 factorial is 336. We need to confirm that this ends up being the same thing. So if I were to take 8 times 7 times 6 and multiply those, sure enough, I get 336. So this is just a different way to approach a problem like this. We can simplify factorials in the calculator, or we can break them down like this. Okay, let's look at another one. Let's see if we can break this down without the use of the calculator, and then we'll check it in the calculator. So 26 factorial divided by 21 factorial. We know 26 factorial is larger, and we know that 21 factorial is part of 26 factorial. I can confirm that by starting to break down 26 factorial. So pull off the numbers being multiplied until we get down to something that's common. So if I pull off the 26, 25, 24, 23, 22, then I would have 21 multiplied by everything lower than that. That's what's common. So our denominator is 21 factorial. If we break down that numerator into parts, into factors, we eventually get to a leftover of 21 factorial. That common factor can be canceled in numerator and in denominator, and then we're just left with those individual factors we got from pulling those off. So let's see what that's going to be. So 26 times 25 times 24 times 23 times 22, and then remember the 21 and everything below that was canceled. And there we go. So 7,893,600. Now let's confirm that that is correct. In other words, these two things are really the same based on just using the factorial keys. So 26 factorial divided by 21 factorial. And there we go, 7,893,600. Okay, now I did say I was going to show you where this is in the graphing calculator, so let's look at that. Okay, you also have PRB in the graphing calculator, but it's not a button. It's an operation under one of the button menus. So we're going to start it out the same way. Say we wanted to reduce this one using the factorial symbols. I need my 26, so type your 26. You're going to go under the math menu in this case. So I'm going to hit the math menu. Now, depending on how new or how old your calculator is, you may have slightly different options. They may be written slightly differently, but you're looking for something like prob or PRB. It may be written as PRB. You're looking for that submenu. So I'm going to arrow over to that submenu, and then notice option 4 is an exclamation point. It's the factorial symbol. So I'm going to go down and highlight that, and I'm going to hit enter, and it puts it on the home row. Okay, now remember, I'm then dividing by 21 factorial. So divide 21 and then go back in. So math menu, prob, and then 4 factorial, or 4, option 4 to give you the factorial, excuse me. And then hit enter, and we get the same thing. So that's where you can find it on the graphing calculator. It's there, you just have to go a little bit deeper. Now I want to show you the next one to show you why your calculator is potentially limited, because you may be asking, why would I want to take the time to reduce anything by hand when I can just reduce it in the calculator? Well, this is why. So 500 factorial divided by 499 factorial. I think we can confirm that these are big numbers. How do we know they're big numbers? Well, think about what 500 factorial means. 500 times 400 times 300, or sorry, I'm skipping some numbers. I'm skipping a lot of numbers. 500 times 499 times 498 times 497, so on and so forth. Those numbers themselves aren't very large, but when we multiply them together, the output is very, very large, very fast. So for example, just to show you how big or how fast they get big, 500 times 499 times 498 times 497. Automatically, we get to something really big. What this means is scientific notation. It means take this and multiply by 10 to the power 10. Automatically, that's a very, very big number. And notice we're not even very far in. We've only multiplied 4 numbers together, and already we're to a number that's really, really big. So, what's going to happen when we try to deal with factorials that are this large? Well, we know based on what happened for these 2 examples, we can simplify this by hand pretty quickly by pulling off factors and then reducing what's common in the numerator and in the denominator. So 500 factorial, another way to write that is pull off the 500 and then 499, 498, 497, so on and so forth, aka 499 factorial. That's left over, and that matches my denominator. So I can cancel what's common in the numerator and denominator, which means I'm just left with 500. So even though 500 factorial and 499 factorial are both very, very large, all of that just reduces down to 500, which is not large by any means. Now, say you wanted to do this in the calculator. We should be able to do it. So let's see. 500 factorial divided by 499 factorial. Okay, so that's what we've got. Hit enter. Overflow error. In other words, your calculator can't handle it. But it's just equal to 500. Why on earth can your calculator not handle it? Well, the reason your calculator can't handle it is because your calculator, unfortunately, is not smart enough to do this. What your calculator is doing is it's evaluating the first factor, and then it's dividing the second factor. So it's doing 500 factorial, and then it's doing 499 factorial, and then it's dividing them. Those individual factorials are too large for your calculator to handle. So even though we know that this reduces down to a pretty small number, to just 500, your calculator can't actually do that. Now, what about the graphing calculator? Certainly that's more powerful. Surely it can handle it. Well, let's see. So 500, remember math menu, probability, factorial, 500 factorial divided by 499 factorial. Same problem. This is a lot more powerful than that little scientific calculator, but even it can't handle it because, again, it's going one at a time. We saw how big those multiplications got and how quickly they got really big. So even though these 2 factorials reduced to something really small, the graphing calculator and the scientific calculator can't handle it because they can't use a strategy like this. So it is still important to be able to do some things like this by hand. Your calculator cannot be used for everything, and this is one situation where, unfortunately, your calculator just can't handle this. Okay, so we've discussed this particular symbol. This symbol is going to be useful in order to calculate the number of permutations, the number of orderings we can have when we're choosing items and we're arranging them into a group. So the number of possible permutations if R items are taken from N items. Okay, so what does that mean? That means we have a total of N items to choose from, and R is how many items we're choosing. So say we have 10 to choose from and we're choosing 5 of them and arranging them. Well, then N would be 10 and R would be 5. The only way these numbers make sense is if N is the larger number and R is less than or equal to N. So they could be the same, or R is going to have to be the smaller number. So we can take 5 and choose 5. That would be what we did in the textbook situation. So we have 5 to choose from, and then we're choosing and we're arranging all 5. So N would be 5, that's the number we have to choose from. R would also be 5, because that's the number we're choosing and the number we're arranging. Okay. So we can take a permutation where we don't arrange all things in the list. Maybe we're just choosing some of them. We're choosing a subset of them. There's a term we haven't used in a while. We're choosing a subset of them, and then we're arranging those that we've chosen in that particular subset. So the notation for that is going to be N, then capital P, and then R. So N is the number we have to choose from. R is the number we're choosing. This is going to be equal to N factorial, so we know what that means now, divided by N minus R factorial. So take the difference between those two numbers and then take factorial. The division of those two numbers is going to give us the number of different arrangements we have if we're choosing R items from the list of N items and then arranging them. So again, R is the number of items being chosen. N is the number of items to choose from. So N is always going to be larger than R, or they could possibly be equal to, but N always has to be the larger number if they are not equal. Now, as with factorial, there is a button on most scientific and graphing calculators to help you calculate these permutations. So here in the notes, I've shown you how you'd simplify everything by hand if you wanted. It's no different than what we did up here. How we simplified things up here is exactly how you'll simplify permutations if you want to count by hand and you want to do it algebraically. Not really count by hand, but simplify by hand. I'm going to allow you to use the button on the calculator for this, and I'm going to show you where it is on the scientific. I'll show you where it is on the graphing calculator. So the trick is just going to be figuring out what's in and then what's R. In other words, how many things do we have to choose from? How many are we choosing? Sometimes it's going to be obvious, sometimes it's not. Sometimes we have more than one step to do in this process of choosing, which means we're going to have to layer in a couple different things that we know how to do. Maybe there's a permutation within the use of the fundamental counting principle. We'll have to see what that looks like when we get there. So let's start with a pretty basic one. So you are coaching a Little League baseball team with 13 players, and you need to choose a batting order that contains 9 players. We want to know how many possible batting orders are there. So think about how many you're choosing and how many you're choosing from. So we have a total of 13 players to choose from, and we have to choose 9 out of the 13, which means 4 of them get left over, essentially. Now, how do we know this is a permutation? Because remember, there's a couple different requirements for a permutation. One requirement is that no item is used more than once, and the other requirement is that the order does make a difference. Well, how do we know this is a permutation? Well, we know in something like a batting order, we can't choose more than once. In other words, when we put one kid in the order, we can't bat him first and bat him last. Unfortunately, it doesn't work that way. So each person put into the lineup only goes into the lineup one time. Okay, so we're not repeating any choices. The order also matters. So the order we bat kids in, if we flip that order, it's a different batting lineup. Think about the Astros. If the Astros change the order of their batting lineup, it's a different batting lineup. The orders are chosen very strategically. So rearranging the elements in the particular arrangement we choose gives a different lineup, what we're going to think of as a different lineup. That's our indication that this is a permutation. So we're not repeating anything that we choose, and the order we choose things in matters. So in this case, our N is going to be 13. And our R is going to be 9. So we have 13, permutation, 9. Okay, now let me show you where this is on the scientific calculator. It's actually going to be close to where we found the probability, I'm giving it away. It's actually going to be close to where we found the factorial button. So just like with factorial, you have to do the number first. You have to do N first here. So you're going to type the 13 first. So 13. And then permutation, the P symbol, we're going to see it as NPR. We're going to see it where it looks like this. It looks like NPR. It's also going to be under the probability button. So PRB, right there, it's option number 1. So NPR. You do have to type the N first. Then you go in the menu, find this, hit enter, and then you're going to type the R, which is going to be 9. So this is saying from 13 items, take 9 of them and arrange them in such a way that one arrangement versus another arrangement, the order things are in matters. And hit enter. Look how big that number is. Let's see how big that is. So count from the right. So 3, so that takes us to the 200. 3, that takes us to the 459, and then 3. So that's 259,459,200. Just for a little league batting lineup with 13 players. There are almost 260 million ways to order the kids in the batting lineup. Think about what it's like for the Astros. They don't play everyone at the same time. A lot of people stay on the bench, or they only play maybe one game a week, something like that. Think about how many they have to choose from for their batting lineup. They've got more than 13 to choose from. So think about something like that. These numbers get really big, really, really fast, which is kind of interesting. It makes these problems kind of interesting. So that's going to be the number of lineups we have, 13, permutation, 9. Now, if you want to do this on the graphing calculator, again, where you find the factorial button, you'll find this as well. Now, you will run into one of two situations with how you type this in, depending on how old your calculator is. So my calculator is fairly new. If you have a newer graphing calculator, you don't have to type the 13 first. You just go find the permutation button. So I'm going to go to Math, Probability, and then the second option says NPR. That's the one we want, and I'm going to hit Enter. Now mine is newer, so notice what it does. It actually has little boxes that you can fill in with your N and with your R. If you have an older one that doesn't bring up any boxes for you to fill in, you're going to have to take care of it like we did in the scientific calculator. In other words, you're going to have to type the N first and then go and find this operation and then type your R. So you'll just have to investigate what it looks like for yours. Odds are if you have a newer graphing calculator, you can do it the way I've just done it. Otherwise, you're going to have to do it the way you do in the scientific calculator. So just play around with yours and see what you get. So I'm going to type the 13, and then I'm going to arrow over, and it's going to tab over into the other box. And I'm going to type the 9, and then I can press enter, and it's going to give us the same number, of course. So 13, permutation 9, arranging 9 kids out of 13, about 260 million ways to do that. Okay, let's look at another one. Okay, a corporation has 7 members on its board of directors, and how many ways can it elect a president, a vice president, a secretary, and a treasurer? Now, how do we know this is a permutation? Because this is a slightly different situation than the one previously described. In the one previously described, there was very clearly an order involved. Here, there's an order, but it's kind of an implied order. It's what we can think of as a hierarchy. If there's a hierarchy involved, then there is an implied ordering. So think about what's actually being done. If you think about the actual choices being made here, there are 7 people to choose from, and we're choosing 4, what's the word? What am I looking for? Administrators, executives, something like that. We're choosing 4 people to serve in these special roles. Well, if we pick the 4, we can arrange the 4 according to what role we want them to play. So we can arrange it so one person is president, one person is vice president, one person is secretary, one person is treasurer. Say we were going to seat them in order at the table based on what role they serve. So the person who sits in the first seat is the president, and then the person who sits in the last seat is the treasurer. If we rearrange how they sit, then we're assigning different people to play different roles. So the ordering here does actually matter. If we were to assign each person a seat at the table, in this case, then rearranging where they sit changes the actual ordering. The arrangement makes a difference here. Now also, we're going to assume that no one can play 2 roles. So someone can't be both president and vice president. That's what makes this a permutation. So nothing is picked more than once, and the order we arrange things in matters. Now again, there's not really an obvious order like a batting lineup here, but because there is some meaning to the order we put things in, there's sort of a hierarchy in place. That is a version of a permutation as well. So anytime there's a hierarchy in place, that means there's a permutation. If we can think of like a first, second, and third place, that's a permutation. Okay, so in this case, we have 7 to choose from, and we have 4 roles to fill. So R is going to be 4, and N is going to be 7. So what's this going to be? So remember, if you're going to use the scientific calculator, 7 first, PRB, NPR for permutation, and then we're choosing 4. So that's going to be 840. So we're choosing 4 people out of the 7, and then we're arranging them. There are 840 ways to do that. Okay, next one. In how many different ways can a police department arrange 8 suspects in a police lineup if each lineup contains all 8 people? So we have 8 people to choose from, and based on this problem, we're choosing all 8. So we have 8 to choose from. That means N is going to be 8. But because we're arranging all 8, that means R is also 8. So N is 8, so 8, permutation, and then we're choosing all 8 of them, so R is 8 as well. So that's going to be 40,320. In other words, if you have 8 people in line, there are over 40,000 ways to arrange those 8 people if you want to put them in a specific order in line. 40,320. Okay, let's look at another one. 5 singers are to perform at an open mic night. One of the singers insists on being the last performer of the evening. If this singer's request is granted, how many different ways are there to schedule the appearances? Okay, now we've got to think a little bit more deeply about this, got to be a little bit more careful. So we have 5 people and we're arranging them. So 5 singers, they're all going to sing, we're putting them into an arrangement. Going to have a lineup. Now one of the 5 says, I have to be the last performer. I'm not going to do it unless I can be the last performer. We want to assume that we've decided that this person can perform last. So if you think of there as being 5 performance slots, what have we now done? We've assigned the person to the last slot. So how many are left? Well, there's 4 slots left. There's 4 slots left to fill. And there's also 4 singers left to assign to those slots because that one person has already been put in place. That means we're not ordering all 5 people. One person we've already taken care of. We've already made sure that person is going to perform last. So we have 4 spots to fill, and we have 4 remaining singers to fill those slots. So that means we have 4 to choose from, 4 singers to choose from, and we're choosing and we're arranging all 4 of them. So it's going to be 4, permutation, 4. So 4, permutation, 4 is going to be 24. So there are 24 different lineups. Now that's assuming, again, that we already determined where that one person is going to go. And one thing I want you to keep in mind, it said this person was going to perform last. It doesn't matter that they chose to perform last. Suppose the person had decided they wanted to perform first, and maybe they have something to do later in the evening, they've got a couple gigs and they want to get it out of the way and do it first. That does not change the problem. What we're worried about is how many do we have to choose from and how many are we choosing and ordering. It doesn't matter which specific order or which specific slots we still have available. If, say, the person wanted to go first, well, we still have 4 slots to fill. Say they wanted to go in the very middle. There's 5 slots. Maybe they wanted to go third. Well, we still have 4 slots to fill and 4 singers to fill them with. So the fact that this person wanted to go last didn't actually have any influence on this problem. The only thing that mattered was the fact that we were placing them first already. We'd already filled one of the 5 slots with one of the 5 singers. That's what made a difference in this case. So you're going to have to be careful when you read these ones. Sometimes there are additional restrictions on the situation. You have to think about what that does. So when in doubt, if you're thinking of it as a step-by-step process, it's not a bad idea. For instance, in this situation, you're filling 5 slots. Well, draw yourself 5 lines and determine how many different ways there are to do what you need to do. We're determining one person is going to go last, which leaves us with 4 slots to fill and 4 people to fill them with. And that's going to tell you that it's going to be 4 permutation 4. Now let's look at another one that's kind of similar to this. So a camp counselor and 6 campers are to be seated along a picnic bench. And how many ways can this be done if the counselor must be seated in the middle and a camper who has a tendency to engage in food fights must sit to the counselor's immediate left? Okay. Now again, don't be overwhelmed by this specific arrangement. They need to be in this specific place. The important thing is we've taken 2 people and we've sat them down first. Okay, that's the important thing. That's the big takeaway here. It means we only have so many additional people to seat. Well, let's think about how many people we have in total. We have a camp counselor and 6 campers, so there's 7 people in total. Okay, so the counselor and the problem kid have already been seated. It doesn't matter, again, where they've been seated. Maybe they could be seated at the end. In this case, we've said we're seating them in the middle. But again, that doesn't actually make a difference. The fact is we've chosen 2 people and we've fixed where they are. The question then is, regardless of where they're sitting, how many slots are left, how many seats are left, and how many people are left to seat? Well, if there were 7 people to start with, we've already seated 2 of them. So that means we have 5 people left to seat, and we're going to assume that everyone wants to sit. We're going to make sure everyone has somewhere to sit. So 5 people to seat and 5 seats to sit in. So 5 permutation 5. So 120. There's 120 ways to do it. Surprisingly enough, this problem and the textbooks on the shelf problem are actually the same problem. They don't look like it, but they really are. Here we're arranging 5 textbooks along a shelf. Pick one for the first spot, the second, the third, the fourth, the fifth. Well, this situation sounds a little bit more complicated, but it's actually the same thing. We have 7 spots. We've already chosen to seat 2 people in a specific spot, which means all we're really doing, the only actions we really have to take, are the actions needed to seat the remaining 5 people, which is the same thing as arranging those 5 textbooks. Same kind of thing. It's just disguised in a different format, but it's the same kind of problem. Okay, let's look at a special case. This pops up from time to time, not super frequently, but specifically if we're talking about letters or numbers, we have to deal with the possibility that there are duplicates. In other words, say we have specific things to arrange, but some things look the same. As in, if we reordered, if we flip the order of maybe 2 or 3 things because they look the same, it doesn't really change the ordering. So whenever we have duplicate items in our list, we have to take into account what that's going to do. So when there are some identical items in the group, things that look the same, the number of permutations decreases because, quote, different orderings may appear to be the same. So say we have 2 A's, for instance, and we want to arrange letters. Well, A1 versus A2, unless they're labeled that way, we can't tell the difference if one is in one spot and one's in another, or if we flip them. It looks the same for all intents and purposes. So the number of permutations of n items, so we still have our value for n, that's still the number of things that we have to choose from, okay? P are identical, Q are identical, R are identical, so on and so forth. So think of those as subsets of items that look the same. So maybe we have 2 of one type of letter, 3 of another type of letter, something like that. Those are sets of duplicates. We're looking for the sets of duplicates. If we want to determine how many ways we can create a permutation of these items, taking into account that some of the items look the same, it's going to be n factorial divided by, take all of those subgroups, take the factorials of those, and then multiply all those together, and that's going to be our denominator. Now keep in mind, in this formula, it's implied that all items in the group are chosen and arranged. If we're only choosing some of them, then unfortunately we don't really have a formula to take care of that. That's actually a fairly complex situation. So we're going to assume in these situations where there are some duplicates that every single thing we have to choose from, we are in fact choosing and arranging. We're just taking into account things that look the same and which arrangements are going to look the same. Okay, so for example, in how many distinct ways can the letters of the word Dallas be arranged? Well, this is a little bit different than arranging textbooks, arranging campers. All the campers are different, all the textbooks are different. Here, some of the things that we're arranging actually look the same. Well, what looks the same? We have 2 A's and we have 2 L's. They all look the same. So we have 2 sets of duplicates. Now the letter D, the letter S, there's only one of each of those. So rearranging those, in fact, makes something that is different. But if we, for instance, took these 2 L's and flipped the order of the L's, it's still the word Dallas. It doesn't look any different. We can't tell the difference between L1 and L2, and if we flipped them, anything like that. So in this case, we have 2 A's, so we have duplicate A's, and 2 L's, we have duplicate L's. So we have 6 letters in total. We're arranging 6 letters in total. So that's going to be 6 factorial. And then we have 2 sets of duplicates. Each of them has 2 elements in the set. So we're dividing by 2 factorial because there are 2 A's. And then 2 factorial because there's 2 L's. We're taking the product of that. Now there is no button on your calculator for this. You will have to do this just using the factorial buttons. But in this case, our numbers are small enough that we can do this in a pretty straightforward way. So we're taking 6 factorial divided by 2 factorial, 2 factorial. Now, notice that both of these are in the denominator. So I'm going to have to be careful when I type this in. I want to make sure my calculator knows that both of these are supposed to be in the denominator. So before I type them in, I'm going to put parentheses around them. If I don't, what the calculator is going to do is it's going to divide the 2 things that are next to one another and then take the result of that and multiply, which is not really what we want it to do. We want to make sure that everything in the numerator is what we're dividing into, and everything is the denominator. Everything in the denominator is what we're dividing into it. So for that denominator, we want to put parentheses around it. So 2 factorial times 2 factorial, and then all of that is in parentheses, which indicates that that's the whole denominator. So I do that division, that's going to give me 180. So there are 180 ways to arrange these letters, taking into account that the A's look the same and the L's look the same. Now, say I had a word that had 6 letters and they were all different. Well, that would just be 6 permutation 6. If they all look different, then any arrangement is different from any other. So what if that were the case? Well, then that would be 6 permutation 6. And notice it's quite a bit larger. That's because we don't have this issue with these duplicates. The duplicates make it so that flipping the L's or flipping the A's in any particular ordering gives me an ordering that really isn't different. If all the letters are different, then any rearrangement is different from any other rearrangement. So the number of arrangements is going to be higher. Okay, what about the word Mississippi? This is a long one. Okay, we have duplicate I's, duplicate S's, duplicate P's. The only thing that isn't a duplicate is M. Okay, so the I's, we have, count them, 1, 2, 3, 4 I's. We have 1, 2, 3, 4 S's, and then we have 2 P's. So we have 3 sets of duplicates, 4 in the first 2 sets, and then 2 in the last set. Now in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters to arrange. So our numerator is 11 factorial. And then we're dividing by the factorial of each of the sizes of these sets. So how many duplicates we have of each type. So 4 factorial, 4 factorial, 2 factorial. So let's do that one. So 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. And again, make sure you put parentheses around that. All of that is intended to be the denominator. Wow, big number. 34,650. That's the number of arrangements of the letters Mississippi. Again, considering the fact that I, S, and P are repeated. So any arrangement of the duplicated I's, the duplicated S's, the duplicated P's is the same as any other rearrangement where the same types of letters are in the same places. Now again, what if we had a word that had 11 different letters? That would be 11 permutation 11. Much, much bigger. So 800, 916, that's 39 million. 39,916,800. That's if all the letters are different. Notice how much bigger that is. It makes a big deal having all those duplicates. This is still a lot of arrangements, but this is quite obviously quite a bit more. Okay, same thing for letters, same thing for numbers, same kind of idea. It doesn't matter what we're duplicating, we're looking for how many duplicates there are. So in how many ways can the digits and the numbers 5,432,435 be arranged? So what's duplicated here? Well, the only thing not duplicated is that 2 in the middle. So we have 2 5s, we have 2 4s, we have 2 3s, and we have 7 letters, or 7 numbers, 7 numbers in total. So count up and make sure you haven't missed anything. So 2 5s, 2 4s, 2 3s, and the single 2, that gives us a total of 7 digits. So 7 being arranged, 7 factorial, 3 categories of duplicates, each of a size 2. So 2 factorial, 2 factorial, 2 factorial. Okay, so that's going to be 7 factorial divided by 2 factorial times 2 factorial times 2 factorial, 630. And again, as you can imagine, if all the digits were different, think like a phone number. If the phone number had all different digits, since phone numbers are 7-digit, rearranging them, think about how many different ways there are to rearrange that. Well, if assuming we don't have the 0 or 1 is the first, we determine that there are, 8 million different ways to have a local telephone number. Quite a bit bigger than 630. So keep in mind, this idea with duplicates is a big deal. It does make a major difference. Having duplicates versus not having duplicates majorly changes the numbers in terms of how many ways we can order things. Okay, so just to recap, a permutation is just a way of choosing such that we're not repeat choosing. In other words, we have a list to choose from. We're only choosing each thing a maximum of 1 time, and we're then rearranging. We're specifically arranging the items we choose. So one arrangement versus another makes a difference. So next thing we'll talk about is what we call a combination. A combination occurs when we're choosing, but the order doesn't matter. So as you can probably imagine, if the order does matter, we end up with a lot more situations than if the order doesn't matter, and that'll be the next video we'll look at.